Now we're going to look at another set of data that needs transforming to straighten it out. In this example, a student opened a bag of M&Ms, dumped them out, and ate all the ones with the M on the top. When he finished, he put the remaining 30 M&Ms back in the bag and repeated the same process over and over until all the M&Ms were gone. So, it has an M on one side and not on the other, so if the M side was up, he ate them and put the rest back in the bag. So here's the table showing the results. After one trial, there were 30 left over. After two, there were 13 left over. After three, there were 10 left over, and so on until we got down to 0. So I'm going to take a look at the calculator and see a scatter plot of this data. So here's what the scatter plot of the data looks like. We can see that it has that characteristic, it has a downward shape, just like very similar to the problem that we had before, only now we know two different types of equations that have that shape, either an exponential, decreasing exponential, or an inverse power relationship. So we're going to try both and see which one fits the data the best. So I am going to do a couple of different regressions. So you'll see here, if you see here, I have the log of the trial and the log of the M&Ms, but I do want you to notice that I took off the 7th one that was 7,0, because you can't take the log of 0. So I just removed that. We're going to do the regression, we're going to do the transformation without that one data point, which is perfectly fine to do under the circumstances. And I'm going to use natural log just to show something different than log, which I did before. So if I add a data and statistics page, we're going to try the log version first. So we did log of trial, and this is actually natural log. I just typed it as log instead of natural log, which I probably shouldn't have done. Okay, so we see here still a slight curve in the data, but much straighter than it was before. Let's take a look at a regression and then look at the residuals. So if we do a regression, you can see it fits pretty well. If there are residuals, it looks like they'll be pretty small. Well, there are residuals, but they're going to be fairly small ones. Residuals, residual plot. Okay, the only matter of concern is the residual plot does seem to have a fairly distinct bend in it, kind of going up and then coming back down again. So let's check the other one, see if it's any better. Sometimes you do a couple of different re-expressions and all of them seem to have a bend in the residual plot, and notice the residuals are very small, so it's not a huge deal. The biggest residual is about 0.5, so it's not really that big. And so this would probably still give us a pretty good representation of the data, but we can always try for something a little better. So we're going to try the other re-expression and see if it works any better. So here I'm going to do trial versus log of M&Ms. Okay, that seems a little straighter. So if we do a regression on this, we'll do a regression. And does seem like it fits more, it has a straighter look. We'll do the residual plot. And this one I really like a lot better. We see a much more scattered residual plot. We don't see that distinct bend. So this seems to be the better model, is to use the exponential model where we take x versus log of y instead of log of x, log of y, which is the power model. So one last check is I'm going to do a linear regression of both of those. So if I go and add a calculator page, I'm going to do a linear regression both. So statistics, stat calc, linear regression. I'm going to do one of log trial, log M&Ms. And notice here we have a nice strong R squared value of 0.92 about, and an R value of negative 0.96. Very strong, very good. Now we'll do the other one. Statistics. Here we go, linear regression. This time we'll do trial and log of M&Ms. As strong as the other one was, this is stronger. We have a 0.98 R squared and a negative 0.99 R, nearly perfect fit. So this is even stronger. So based on the scatter plot, the residual plot, and the R and the R squared values, it definitely looks like the exponential model where we do x versus log of y is a better choice for our model to re-express the data. So going back to here, I'm going to kind of get rid of a couple things, and so we can see what I did here. And maybe I'll put this back up and kind of do this a little time. So I have the original data. Could be either exponential or power, based on the look of the scatter plot. I tried power, which was log x log y. I tried exponential, which was x log y. We saw that this was a better fit. I also checked the correlation for both and the r-squared value. So it says here, explain why it would be reasonable to use an exponential model to describe the relationship between the number of M&Ms remaining and the course number. And by the way, for some reason, the people the original worksheet that I got this from used the word course instead of trial. I prefer the word trial, but I forgot to change it anywhere except in the original table. So everywhere I'm going to have to go through and change this. So we have a better linear fit based on the residual plot and the correlation. Also, since M&Ms are two-sided with M&M on one side, we expect to take away about 1/2 of them each trial. Multiplying by 1/2 each trial is an exponential pattern. Okay, so that actually makes more sense to be an exponential pattern. Okay, now we're going to look at the next piece. Says give an equation of the least squares regression line. All right, so here's my linear regression that I did using the trial and log of M&Ms, and I made a note that it says log here, but I actually used natural log, which is also the same thing that was done here. You can see some numbers in common, so you can see here, here's the y-intercept, here's the slope, here's the y-intercept, and here's the slope over here. And I guess that's all we need for this. You can see the r-squared values are the same, right there as well. Okay, so when I write the equation, it's natural log of M&Ms equals 4.0593 minus 0.68073 times the trial. Okay, so there's my y-intercept and my slope. If I want to predict the original amount of M&Ms in the bag, that would be trial 0. In other words, before I've dumped any amount, that would be trial number 0. I'd put 0 in. That would be my y-intercept. Well, this y-intercept, though, is the natural log of the M&Ms, not the actual number of M&Ms. To find the actual number of M&Ms, I have to remember that natural log is log base e. So I have to take e to this exponent in order to find the actual number of M&Ms, which was about 58. So when you're dealing with natural log, you have to take e raised to the exponent here in order to get back to the original data values. The next part asks me to make a 95% confidence interval for the slope of the least squares regression line. So I'm going to try to get up where I can see this data up here. Remember, when we do a confidence interval for the slope, we use the sample slope plus or minus the t-critical value times the standard error of the slope. The standard error of the slope is right here on the computer printout. When we do a linear regression t-interval on the calculator, it also gives us the standard error of the slope right here. Now the t-critical value can be gotten from either the table or using inverse t with 0.975. If you use the table, you go to 95% confidence. Degree of freedom equals 4. The original number of data values was 7, but remember when I did my regression, I only used 6. So I'm using 6 minus 2 to get my degree of freedom here. And so there's the t-critical value, there's the standard error of the slope, and you can see here's the upper and lower level of the confidence interval right here, and those are the values that I used for these two values here. Now when you interpret it, remember, you've got to be careful. You're still talking about natural log, or number of trials and natural log of remaining M&Ms. So I am 95% confident that the interval from negative 0.81273 to negative 0.54872 captures the true slope of the regression line relating the number of, probably should have said number of remaining M&Ms to the trial number. So it's relating the natural log of M&Ms to the trial number, not the M&Ms. So be careful, you have to interpret it that way. Now the last question says, super fun bonus question. In theory, the number of M&Ms remaining after each course should be half of the number left after the previous course. Is your confidence interval in part E consistent with this theory? Okay, so it makes sense that if there's an M&M on one side and you just randomly toss the M&Ms, that about half the time the M&M will be up and you'll take it away. So you should take away, theoretically, half the M&Ms each trial. If we are looking at the original equation, that half would show up right here. In other words, the equation of our line should be about this. Y equals the original number of M&Ms, which is about 58, times 1/2 to the x power. So we would expect that that we start with 58 and we lose about half each time. That should be basically what our equation looks like. So that B value, which shows up down here as log of B. So our slope is actually, then in this case, the natural log of 1/2. It should be our slope should be about natural log of 1/2, and we found a confidence interval for the slope. So so I've kind of summarized this. The slope is natural log of B. So our confidence interval gives a plausible range of values for natural log of B. We would like to find a plausible range of values for B and see if it's close to 1/2. So we are going to solve natural log of number of M&Ms equals -0.81273, the left-hand value of our confidence interval, and natural log number of M&Ms equals -0.54872, which is the other side. And we just want to find what number of M&Ms is. So we are going to say number of M&Ms is e to this exponent, number of M&Ms on the right hand side is e to that exponent. So the actual B value here, which should be close to 1/2, this is B. So these are our plausible range of values for B. So we're going to say 0.4436 less than B less than 0.5776. So we're 95% confident then that B in the original exponential equation is between these two numbers. And since that interval contains 0.5, okay, since that interval contains 0.5, it is consistent with the theory that half the M&Ms are removed and half remain after each trial. So very interesting problem, showing a lot of theory about why we use natural log and so forth, but also just the basic techniques of sometimes you take the log of both variables, sometimes the log of one variable. Just trial and error sometimes is what you have to do to figure out which is the better transformation.